In the name of Allah, the most beneficent, the dispenser of grace. My name is Muhammad Osama, and today I'm here to express my views on the topic of balance trees, AVL search trees, insertion and deletion in an AVL search tree, B negative trees, searching, insertion and deletion in a B negative tree, B positive trees, red-black trees, and Splay trees. We have a number of variety of trees here, which we are going to be study in data structures and algorithms. We will discuss its some of the advantages and some of the disadvantages, which will be mentioned in these slides, and we will see that which tree is more accurate, more good for the searching purpose, for insertion purpose. So let's get started and look at the slides. Okay, while starting the topic of the tree, we must know what is a tree in data structures and algorithms. So here is a simple short definition of a tree in data structures and algorithms. A tree is a non-linear hierarchical data structure that consists of nodes connected by edges. Here we are seeing the definition of a tree. As we see trees in our daily life, they are non-linear. They are non-linear hierarchical, means to say that their branches are not linear. They have different branches connected to nodes, and they have different edges that are not non-linear, that are not linear, and they are hierarchical data structures. So an example of tree is mentioned in this slide. A simple tree diagram is mentioned in this slide. Okay, let's move to the first type of the tree, that is the balanced tree. While looking at the definition of the balanced tree, we come to know about a balanced tree is referred to as a height balanced binary tree. Means to say its height is balanced, and it is defined as its height of the left and right subtree of any node differ by more than one. It's one of the important factor here is that its height is adjusted and it's not more than one. As we look at the pictures which are mentioned in the slide, the difference height is not more than one. So this was about the balance tree. Actually, there is a problem. There is a disadvantage of a balance tree. So the next tree which is introduced is the AVL search trees. AVL search trees got its name from its inventor, that is George Adelson Velasquez and Landes. So what's about the AVL search trees? If we look at the definition of the AVL search tree, we have come to know about an AVL tree is a self-balancing binary search tree. Means to say its nodes or its edges are self-balanced, in which each node maintains extra information. Each node has some extra information that is called a balance factor, and uniquely its value is either -1, 0, or +1. So this was all about the AVL search tree and its uses. Coming to the furthermore, it has some disadvantages. So further new trees are introduced which has good time complexity, that are different trees we will study in further slides. So we will look at how the insertion and deletion in an AVL search tree is happened. While talking about insertion, in the first step, to make sure that the given tree remains in AVL after every insertion, we must augment the standard binary search tree insert operation. So we have to follow some operations in which we add some standards in binary search tree, and we perform the rebalancing technique. And following are the two basic operations that we can perform to rebalance trees. That is, the keys left is smaller than key root, and that is smaller than keys root. And there are two type of rotations which we can implement in the insertion process. That is the left rotation process, and second one is the right rotation process. And this was all about that how can we insert some arguments, or how can we insert something in AVL search tree. Okay, look at the process of deletion in an AVL search tree. To make sure that the given tree remains AVL after every deletion, we must have to augment the standard of ST. Operations to perform some rebalancing. So in deletion process, as we done in insertion process, we have to augment some standards which are operations for the rebalancing for the deletion process. And following are the two basic operations that can perform to rebalance a binary search tree without violating its property. And that is, keys left is smaller than keys root, and that is smaller than keys right. And here we can do two types of rotations to perform the deletion in an AVL tree, that is the left rotation and the right rotation. And here is some pictures that explain how an insertion and deletion in an AVL search tree is happened. Okay, moving to the next tree, that is B negative trees. There is a good time complexity process and good algorithm process furthermore in B negative trees than in AVL search trees. So looking at the definition of B negative trees, it's also a self-balancing search tree. One of the most good feature of the B negative trees that it's a self-balancing tree like search trees like AVL and red black trees, and it is assumed that everything is in the main memory. Okay, while looking at the use of binary trees, B negative trees, we must think that huge amount of data can not fit in main memory. As we know that a vast amount of memory cannot be stored in the main memory, so we use the B negative trees, and when we number and when the number of keys is high, the data is read from disk in the forms of blocks. So actually the B negative trees uses blocks to store some sort of data, and the algorithm for using the search tree is mentioned here. The time complexity for search is big O log n, and the time complexity for insert is big O log n, and the time complexity of delete is also the same as big O log n. The picture of B negative tree mechanism is also shared on this slide. So there is some disadvantages furthermore for B negative trees. We will discuss some more trees that has good time complexity and good algorithm more than B negative trees. We will discuss some insertions and deletions and searching in B negative trees in next slide. So while looking at the searching process and insertion process and deletion process of the B negative trees, if we talk about the searching process, the search operation in the B negative trees is the simplest operation. And if we talk about the insert operation in B tree, that is the self-balancing tree, You cannot force to insert a key into just any node. And if we look at the operation of delete in B negative tree, the delete operation has more rules than insert and search operation, and it seems that it's been more tricky than searching operation and the insert operations. So coming to the point on searching, let the key the value to be the searched by key k, and start searching from the root and recursively transverse down. And if k is lesser than the root value, search left subtree, and if k is greater than the root value, search the right subtree. And this was the mechanism that how can we search the specifically k, and if the node has the if the node has the found k, simply return to the node. And if the k is not found in the node, traverse down to the child with the greater key. So this was all the mechanism of the searching, and if there is if that thing is not found, then we return to the null value. Okay, while talking about the insert operations, we will run the search operation and find the appropriate place where we can insert some of our some sort of our value. Insert the new key at the proper location. We will insert the key at the proper location where it used to be. But if the node has a maximum number of keys already, so what will we do there? We will do the node along with newly inserted key will split from the middle element, and the middle element will become the parent for other two child nodes. And this was all about the insertion operation in the B negative trees, and the nodes must rearrange the keys in the ascending order. And this is also an important point, that the keys will rearrange themselves in the ascending order. At the end, we will talk about some deletion operation in B negative trees. So for this purpose, run the search operation and find the target key in the node. And this is an important step. And the three conditions applied based on the location target key as explained in the following sections of insert operation and the searching operations. So this was all about the searching, insertion, and deletion in B negative trees. So let's talk about some important features of B positive trees, as it is furthermore good and sense of time complexity than the B negative trees. So if we talk about the a B positive tree is an advanced form of self-balancing tree. An advanced form. It's a good form than B negative trees, in which all the values are present at the leaf level. This is an encanting feature of the B positive tree, that all values are present at the leaf level, and all values will be stored at the leaf level. An important concept to be understand before learning B positive tree is multi-level indexing. This is an important feature of the B positive tree. If you learn about the multi-level indexing, then you should learn about how the B positive trees actually works. In the multi-level indexing, the index of the indices is created as shown in below, and a figure of the B positive tree mechanism is also delivered in this slide. It makes assessing the data more easier and faster, and this is one of the most beautiful feature of the B positive trees. Okay, now as I told you earlier, that every tree has some of the disadvantages, so we will further move to a tree that is more good in time complexity and more good in every aspect. So we will finally move to the red black tree. uh, this tree only covers the mechanism of colors, in which we color red, in which we use the color red and black. And this tree was invented by Rudolf Bayer in 1972. So let's talk about some sort of definition of the red black tree. A red black tree is a kind of self-balancing binary tree, as we discussed earlier, that it's also a kind of self-balancing tree where each node has an extra bit. Okay, and that bit is often interpreted as the color red and black. So we use different color, that is the red and black, to interpret a bit. These colors are used to ensure that the trees remains balanced during the insertion and deletions. So these color show that the your bits are in the proper order and they are balanced. Although the balance of the tree is not perfect, it is good enough to reduce the searching time. So this feature reduce the search time and enhance the time complexity and maintain it around the like big O log n time, where n is the total number of the elements in the trees. So this was all about the red and black trees, and this tree has furthermore good complexity than the B negative trees and B positive trees and AVL searching trees. So finally we will talk about the Splay trees, and this was the last tree of our discussion. So take a look at the definition of Splay trees. A Splay tree is a self-balancing tree. As we discussed earlier, that all the trees are self-balancing trees, like AVL trees, the B negative trees, the B positive trees, the red and black trees. So it's also a self-balancing tree. But AVL and red black trees are also self-balancing trees. So we have discussed that the AVL trees and red and black trees are also self-balancing tree, but what is the feature that makes the Splay tree the more unique than the other trees? So here the main important and unique feature is it has one extra property that makes it unique is splaying, and this has a extra property that makes it unique, and that is the splaying property. The figure of the Splay tree is mentioned here, and how it works is some sort of understanding that is mentioned here. Hope you have understand the different types of trees that are used in the data structures and algorithms, and you have also understand the time complexities of these trees and major advantages and disadvantages of the trees. So this was all about today's lecture. If you have any questions or queries, you may ask in the comment section below. And thank you so much for your attention.